Let's look at special relativity and in particular time dilation. So time dilation refers to a difference in time that is recorded by two different clocks that have a certain velocity with respect to one another. Proper time is a time that is measured in the same reference frame in which the event takes place. Here we have a stationary spaceship. Let's say that the spaceship has a width d, and at some point in time, a flash of light will take place over here. It will travel the width of the ship, it will bounce off a mirror, and then it will reflect back to some sort of an observer here. Let's say that there is this barrier so that the observer hadn't seen the flash of light take place, only the reflection of it. So the amount of time it took between the flash of light took place and the observer saw it is delta t naught is twice the width of the ship divided by the speed of light. So then the proper time delta t naught is 2d divided by c, the speed of light. And it is the proper time because the event took place in this stationary spaceship and was observed in the stationary spaceship. Now let's look at a moving spaceship. So here is what's happening in this situation. We have the spaceship at 3 different locations as viewed by an observer somewhere out here. And then the flash of light takes place, it's reflected off the mirror, and then it gets back to the observer. So as the observer from outside the spaceship watches this, it sees that somewhere here on the left there's a flash of light, then the spaceship is moving, the observer notices that the light is going to be bounced off the mirror when the spaceship is over here, and then later on the observer outside of the spaceship notices that by the time the observer in the spaceship saw the flash, the spaceship is already at a different location. So let's say that the speed of the spaceship is constant and it's v. V has to be very large, very close to the speed of light. And the distance that the spaceship traveled from the time that the flash of light took place to the time when it bounced off the mirror is this L. And then the distance traveled afterwards from the time when the flash bounced off the mirror to when the observer in the spaceship saw the light is another L. So then we can say that the distance traveled by the spaceship, which is 2L, with velocity v, took the amount of time delta t is 2L divided by v. But now if we're looking at the distance traveled by the light, we see that the light traveled this path. So in this triangle, using the Pythagorean theorem, this is the hypotenuse, and it's square root of d squared plus L squared. So the light traveled twice that. It's 2d squared, square root of d squared plus L squared. And light travels at the speed of light, so it has velocity c, and it traveled the same amount of time as the spaceship because the light stayed inside the spaceship, so it traveled the same amount delta t. So now we can solve for this difference in time. The delta t is called a dilated time, and this is how we will go about solving for this. So I have from this last line, delta t is 2 square root d squared plus L squared divided by c. And I will find L from here and d from there. So then L is going to be delta t times v divided by 2, and d was delta t naught times c divided by 2. So I'll square those two and plug them into the previous equation. So we have here 2 times square root delta t v over 2 quantity squared plus delta t naught c over 2 quantity squared. And we divide this by c. So how about we multiply both sides by c and divide them by 2? Then we end up with delta t c over 2 is equal to square root of delta t squared v squared divided by 4 plus delta t naught squared c squared divided by 4. Multiplying both sides, or squaring both sides, we end up with delta t squared c squared equals delta t squared v squared plus delta t naught squared c squared. So I canceled out the 4 on the bottom there, and now I can factor out the delta t squared from here, end up with delta t squared times c squared minus v squared equals delta t naught c squared. And when we rearrange terms and solve for delta t, we end up with an expression for the dilated time. Delta t is delta t naught over square root of 1 minus v squared over c squared. So if we do the math, we see that v divided by c is less than 1. C is the largest speed attainable. So if we have a quantity that's less than 1 and then we're squaring it too, we're subtracting that from 1, we get a value here that is less than 1. So dividing the proper time by a value that's less than 1 gives us a larger delta t. So that's why we end up calling this the dilated time. Now, one strange thing that comes out of this is what we call the twin paradox. So let's say that you have a set of twins and they are on Earth. One of them decides to travel out in space. So one of them climbs on this spaceship and goes very far, very fast. And when it comes back, that twin measures the time traveled in the spaceship. So the twin says, well, the time that I traveled was delta t naught, or the proper time. The twin that was left on Earth, though, is going to think that the twin that traveled would have had to experience the delta t, the dilated time. So when the twin that traveled returns from Earth, the Earth is going to be older. So the twin on Earth would be older than the twin that traveled on the spaceship. But the paradox is that we can say that the twin on the spaceship was in a reference frame measured with respect to the spaceship. So the twin on the spaceship was stationary relative to the Earth that was moving away from the spaceship and then returning. So the twin on the spaceship thinks that he should be older than the twin on the Earth that traveled. So the paradox arises from the fact that to get a spaceship to such high velocities, the spaceship has to accelerate. So if you remember from a previous lecture, when that happens, then we're dealing with non-inertial reference frames and special relativity no longer holds. We would have to use general relativity to figure this out.